Hello and welcome everyone to today's NPTEL live session on course of Foundations of Cryptography. So let me share my screen first. So actually, if you remember, last week we had some discussion or confusion about one of the assignments. That was question 5 of week 7 assignment. So let me first discuss once about that question, and then I will progress to week 8 assignment questions, and then this week's problem solving session. Okay. So the question was, let E of K and M, and if there is a scheme with encryption and decryption defined, and that scheme has been said to be authenticated encryption scheme. And then we are considering two different constructions. Okay. So first one is defined where encryption is denoted as E1. And there basically we provide a ciphertext C, C, where C is computed using the basic encryption algorithm using key K and message M. And decryption is just decryption of the first part of the ciphertext, that is C1, using the key K. So basic decryption algorithm is run on first part of the ciphertext using key K. And then there was the second construction where encryption algorithm was exactly the same as of the first construction, and decryption algorithm just checks whether the first part is equal to the second part first, and then do the basic decryption algorithm on the first part of the ciphertext using key K. So the conclusion is that basically both the constructions are CPA secure and both provide ciphertext integrity. To prove that, so let us just see the formal argument how we used to prove CPA security of some scheme previously. So if you remember from the initial live sessions, there we used to prove that some scheme is CPA secure by proving that if that scheme would not be CPA secure, then that would break the CPA security of the initial scheme, which we already think that that is secure. Okay. And also another thing to mention, because the basic scheme is authenticated encryption scheme, and if you remember, authenticated encryption scheme means that that scheme satisfies both CCA security and ciphertext integrity. And if a scheme is CCA secure, then that must be CPA secure as well, right? Because CCA security is even advanced concept of security than CPA security. So if CCA security is provided, then of course CPA security is also provided. So this basic encryption scheme with this encryption algorithm E and decryption algorithm D, they are this encryption scheme is CPA secure, CCA secure, and also it provides ciphertext integrity, right? Now using that, if we are arguing that, let us denote this modified encryption scheme, the first construction, with pi1 and our basic scheme as pi. So pi is given as authenticated encryption scheme, and we will analyze the CPA security of pi1. Okay. Now let us first assume that what if pi1 is not CPA secure? Then there must be an adversary A which is able to distinguish encryption of M0 from encryption of M1 after using the encryption oracle service, right? And if there exists such an adversary A, then we can construct another adversary A dash, which will make use of this adversary A and will be able to break the basic CPA security of the basic scheme pi. Okay. Now, the game is as follows. The left part is the game for the CPA security of the scheme pi. So this is the challenger and this is the adversary A dash. And this right half of the game is for the CPA security of the modified scheme pi1. Okay. Now game proceeds as follows. The adversary A provides some message M to this adversary A dash, and A dash forwards that message to this challenger, and as the encryption algorithm of pi does, it just returns ciphertext C corresponding to message M and some key K. So the ciphertext is denoted as C and forwarded to A dash. And what A dash does is that it just provides two copy of C, that is C comma C as the ciphertext corresponding to the encryption scheme pi1 to A, right? And this encryption oracle service runs polynomial number of times, as you know. Next, adversary A chooses two different plaintext M0 and M1. One thing is not written here, which is this size of M0 should be size of M1, which is the condition for CPS security game, if you remember. Okay. Now M0 and M1 are provided by A, and A dash just takes them and forwards to challenger C. And C, as you know, chooses some random bit B from 0 or 1 and just gives the challenge ciphertext CB to A dash. And A dash again takes two copy of CB and makes the ciphertext challenge ciphertext CB comma CB for the scheme pi dash. Pi1. Now, if we are assuming that A is able to successfully distinguish the encryption of M0 from encryption of M1 by seeing the challenge ciphertext, so it is able to correctly guess the bit B, right? So it will return some distinguishing bit B dash, and A dash will get that B dash and just forwards the same B dash to C, right? So as you can see, if A is able to output the correct P value, then A dash is also able to return the correct B value, right? So if B is equal to B double dash, that means that A dash wins. So clearly, the game shows that probability that A dash wins is exactly equal to the probability of A wins. But we already know that this basic scheme pi is authenticated encryption scheme, that is, it is CPA secure. So probability of winning of A dash is already known to be half plus negligible, right? So same will be the probability for winning of A, which is the adversary for scheme pi1. So we conclude that pi1 is also CPA secure, that is any adversary trying to distinguish encryption of M0 from encryption of M1 will have the distinguishing probability. Well, there is one thing, so it just should not be confused, is that probability of winning is actually negligible. Half plus negligible is actually the distinguishing probability, right? So there is this random guess of bit B, which is the probability half. And distinguishing probability, if we say that how, with what probability it is able to distinguish between encryption of M0 from encryption of M1, that probability is half plus negligible, but probability of winning, if we say, that should be negligible, okay? So there is just some notational confusion, okay? So ultimately what we say is that pi1 is CPA secure. And if we see that the second construction is also, the encryption algorithm is exactly same as construction 1. So in terms of CPA security, the encryption oracle access does not provide any extra information in case of construction 2. Hence, construction 2 is also CPA secure. We can easily conclude. Now, about the ciphertext integrity, what was actually the concern in the next week. So, ciphertext integrity game, if we remember, that game proceeds as follows, that there will be some challenger and there will be some adversary. Now adversary provides messages of its own choice and gets back ciphertext for those corresponding messages. And after seeing such polynomial number of message ciphertext pair, the adversary actually tries to output some ciphertext C star, which should be valid ciphertext of some new message. New message means that message should not belong to this query phase messages. Okay. So if it is able to output such valid ciphertext C star, then it wins the game. Now, if we argue that pi2, the second construction, is actually provides ciphertext integrity, then we actually want to show that if it would not have provided ciphertext integrity, then that would break ciphertext integrity property of the basic scheme pi as well. Okay, so similarly, we designed the game with the left part being the ciphertext integrity game for scheme pi and right part being the ciphertext integrity game for the scheme pi2. And then there is this adversary A queries with some message M. A dash forwards the same query to the challenger. Challenger outputs the corresponding ciphertext C. Actually, this C should be also, this is the C for corresponding to message M. And then it just copies the same C, makes 2 copies of C and provides C comma C as the ciphertext. Now, if the adversary A is able to output some valid ciphertext of the form C star comma C star, which actually decrypts to some message which is not seen before by the adversary A, then we just take the first part of that ciphertext, like A dash just takes the first part of that ciphertext, which is C star, and provides to this challenger and wins the ciphertext integrity game in the basic scheme pi, right? Why is that so? Because if you see that here in the scheme pi2, it checks whether C star is equal to, like, the first part is equal to second part, and then runs the exact same decryption algorithm as of the basic scheme. Okay, so if A is able to output such valid ciphertext, then taking the first part of the ciphertext C star will result in some valid message only. So decryption of C star comma C star is exactly equal to decryption of C star, provided that these 2 parts are same, right? So this scheme pi2 provides ciphertext integrity. And what about the scheme pi1? That would also provide ciphertext integrity, because although there is no check on C1 equal to C2 or not, anyway, if whatever the adversary A, like if you think in terms of the game pi1, where decryption algorithm is exactly same, apart from that, there is no check whether C1 is equal to C2 or not. Now, in that case, this pi1 part of the game, here A would have returned C star comma any other like whatever member of this ciphertext space it wants, it can provide. But if it correctly decrypts, that means the decryption of the first part actually results in some valid message, means which is a new message. And then just giving the first part as the output ciphertext in the game pi, that would also decrypt to same message M, which is a valid message. So that means if A is able to break the ciphertext integrity of pi2, then A dash will also be able to break the ciphertext integrity of the basic scheme pi. But pi is already known to be providing ciphertext integrity because it is an authenticated encryption scheme. So we conclude that this scheme pi2, the modified construction pi2, also provides ciphertext integrity, and same goes for pi1 as well. So we conclude that both the scheme pi1 and pi2 provide CPA security, and both the scheme provide ciphertext integrity as well. However, I would just like to mention, to add to this, that the first scheme pi1 actually will not provide CCA security. If you think of CCA security, there the adversary has additional access to the decryption oracle. Now, if you just think on it yourself, you can find out that pi1 actually does not provide CCA security, but pi2 provides CCA security just because of this additional check on C1 equal to C2 or not. Okay, I will not go into detailed discussion about that, but I just wanted to add this. Now let me proceed to the week 8 content. So they are the NPTEL questions as posted for week 8. So first was this: select the correct options. Composition of a CPA secure scheme together with a SCMA secure map will always ensure an authenticated encryption scheme. So this is not true, because we have seen actually three different approaches for building authenticated encryption scheme by composing CPA secure scheme and ACMA secure map. Among them, we have seen that if we compose in encrypt then authenticate way, then only we get some authenticated encryption scheme for sure. But apart from that, other two approaches, which are authenticate then encrypt and authenticate, these two approaches are not always guaranteed to provide authenticated encryption scheme. So first first statement is actually incorrect. Okay, so it depends on how you are composing those two schemes, CPA secure encryption scheme and ACMA secure MAC. In general, we cannot say that it would be true. Coming to second statement, if message M is made up of a sequence of blocks M1 to MD and MAC algorithm outputs a set of tags T1 to TD respectively for each of the blocks, then it is easy to forge a MAC on a new message by reordering the tags. So this is like a very basic statement about MAC design. So if you remember, so this is very obvious to see that let's say D equal to 2. So we have just two message block M1, M2, and MAC algorithm outputs a set of tags set of pair of tags T1, T2. So T1 corresponding to M1 and T2 corresponding to M2. Now, just seeing these two valid message pair tag, the adversary is able to come up with a new valid message tag pair, which can be M2, M1 and corresponding tag being T2, T1, right? Which is again a actually a valid message tag pair, right, on a new message. So reordering the tags is possible at a course. So this statement is true. Coming to third statement, choosing separate keys for encryption and authentication is not needed if the correct order of encryption and authentication is chosen to obtain a secure authenticated encryption scheme. This is actually wrong. So basically, separate keys should be chosen. Like you have the key space for encryption algorithm, like encryption scheme, and you have the key space for authentication scheme. You should sample the encryption key and authentication key independently of each other from the respective key space. Even though it is possible that the key space are same for both the scheme, but using exactly the same key may lead to some kind of security breach. Okay, so it is not necessary that always it will be the case, but depending on the particular choice of which encryption scheme you are taking during composing and which MAC scheme you are taking, so depending on that, it may be the case that sometime it may lead to vulnerable design of authenticated encryption scheme. So just for an example, you can try with like your encryption scheme is a CBC mode of encryption and your MAC is also CBC MAC. There it might be the case that using the same key K for both encryption and authentication may lead to security vulnerability. Okay. Fourth option, padding oracle attack is based on the error response sent by the receiver. So this is very true because padding, if you remember from the last session, so padding oracle attack is actually exploits the fact that when receiver returns the bad padding error. Okay, so in the CVC mode of designing CVC mode of block cipher, so there last block, if your length of the whole message is not exact, is not the multiple of block length, then you add some padding bytes in the last message block, right? And in case this padding is not properly done, then the receiver will return bad padding error, and adversary just seeing this bad padding error that is exploiting this padding oracle, it can effectively calculate back the whole message block itself. Okay, so anyway, so basically this statement is true. Okay, let me proceed to the next question. So only correct option here was the second option and the second statement and the fourth statement are correct. Next question, which of the following is or are correct for the key exchange problem? The goal of the sender and receiver is to agree upon a random common key over a public channel. This is true. Stronger security notion of key exchange protocol requires the adversary to be unable to distinguish between the output key and the uniform random element from the key space, except with a negligible probability. So this is true. If you remember, so basically, what is key exchange protocol? There will be two parties. Basically, each of them will run some protocol, or they will individually run some algorithm. They will exchange some information between them, but any third party who is observing this communication between them will not be able to guess the output of the final key which they are deriving by running the key exchange protocol locally. Okay, so that key cannot be guessed by seeing the communication between them. So the whole set of communication between two parties during running the key exchange protocol is called transcript. So we say adversary, even after seeing the transcript, is not able to guess the exact output of the key exchange protocol. Okay, what is the key at the end of the protocol? Now there are two security notion. One is weak security notion, another is strong security notion. In case of weak security notion, we say that it is hard for the adversary to guess exact value of the key, and in case of in case of weak security notion, we say that it is hard for the adversary to guess the exact output of the algorithm or exact key. And in case of stronger security notion, basically, if the adversary is provided with either the exact key or some uniform random element of the key space, then adversary cannot distinguish between them. That is the strong security notion. So the second statement is clearly a true statement. And fourth statement also, if you see just now, I just discussed. So with the security notion of key exchange protocol requires the adversary to be unable to compute the key output key except with the negligible probability. So second and fourth statement is clearly true. And what is the third statement? The goal of the sender and receiver is to agree upon a fixed common key over a private channel. The channel is of course public, no doubt about that. And about this random common key or fixed common key, the thing is that each time you run the key exchange protocol, you may output different key from the key space. So that key will be common, generated by both sender and receiver will generate the same key. So the key will be common, but each time you run the protocol, it may be random. Okay, so that is why it is not fixed, it is random common key. Okay, so only incorrect statement is the third statement here, rest of them are correct. Next question. Let sender and receiver have a pre-shared random and private AES key K. Then consider the following method of authenticating messages of size, which is a multiple of 64 bits, to authenticate a message M, which is collection of 64-bit blocks, and number of blocks are less than equal to L. Okay. Then the tag generation algorithm outputs T equal to some T1 to TL as the tags. So L number of tags corresponding to L number of message blocks, where Ti equal to AES of Mi concatenated with the integer representation of L. Okay, with respect to key K. Here L denotes 64-bit integer representation of L, as I said. Accordingly, the tag verification algorithm performs the corresponding verification step and identify the correct statements from the following. Above MAC is randomized and hence is SCMA secure. Above MAC is deterministic and hence is CMA secure. Above MAC is neither CMA secure nor SCMA secure. Then it is said above MAC when used in encrypt and authenticate approach leads to an authenticated encryption scheme, and then the adversary can always win the MAC forgery game. Now, if you see that, let us take like any let us take that there is two messages. So the adversary, let's say, sees the tag corresponding to message block M1, M2. So the tag will be calculated as T1 equal to AESK of M1 concatenated with 2. That is the 64-bit representation of 2, and T2 will be AES with respect to key K and M2 concatenated with the 64-bit representation of 2. Now, if you see, if we are now try to generate a valid message ciphertext pair corresponding to message M2 M1, okay. So what we have seen till now is the tag for M equal to M1 M2 and the corresponding tag to be T1 T2. Now we are trying to output a valid message tag pair as M2 M1 and corresponding tag T2 T1. So clearly, this will be a valid tag for the message M2 M1 because T2 is indeed a valid tag corresponding to message block M2, and T1 is indeed valid tag corresponding to message M1. Okay, so so we can say that yes, the adversary is actually able to come up with valid message tag pair by reordering the messages and tags. So this MAC scheme is neither CMA secure nor SCMA secure. And then as the MAC is not secure, so that MAC cannot be used in the encrypt and authenticate approach as well. So if used, then it would not lead to an authenticated encryption scheme. So basically, correct statements are that above MAC is neither CMA secure nor SCMA secure, and the adversary can always win the MAC forgery game because adversary is always able to reorder the message tag pairs and come up with a new valid message tag pair. Next question, select the correct options. A cyclic group has one or more generators. Of course, this is true. That is what this definition of cyclic group says. So cyclic group has one or more generators. Group Z5 with respect to binary operator addition modulo 5 has 5 generators. So this is not true because the modulo 5 is a prime number. So this is a additive group Z5 with prime order. But for the prime order group, if you remember that except the identity element, all other elements are generated. So basically here 0 is the identity element. So except 0, there are 1, 2, 3, 4 elements which are generated. So the truth statement would be that Z5 with respect to binary operator addition modulo 5 has 4 generators, not 5. Then the order of group ZP star with respect to multiplication modulo P, where P is a prime order. So this statement is not true because as you know that the number of element in ZP star is actually P minus 1. So although P is prime, the order of the group is P minus 1, which is not necessarily prime. And the last statement, 46 to the power 51 mod 45 equal to 46. This is true. We will see how. So correct statement here. Okay, and this meeting will end in 10 minutes. And we can join in the same link once it ends. Okay, so first statement was correct and last statement is also correct. So let me just go through the explanation first. So we need to calculate 46 mod to the power 51 modulo 55, right? So modulo 55 can be like 55 is multiplication of 2 prime P 5 into 11, right? So just notice that 46 we can write as 1 modulo 5. That is completely okay, right? Now you raise the both side to the power of 51. So 46 to the power 51 is 1 to the power 51. That is 1 modulo 5. This is clear. Now with respect to 11, 46 is congruent to 2 modulo 11, and also by Farmer's little theorem. So what Farmer's little theorem says is that, say P is a prime, so all the numbers less than P are of course co-prime to P. So you take any number from ZP, and that number, say A to the power P minus 1, will be basically congruent to 1 modulo P. So using that we can write here, we got 2 here, right? 46 is congruent to modulo 11. So 2 to the power 10, because we are dealing with modulo 11, so P minus 1 is 10, and 2 to the power 10, because 2 is co-prime to 11, so we can write 2 to the power 10 is congruent to 1 modulo 11. This relation is coming from Fermat's little theorem. And then here we are using that, we are calculating 46 to the power 51 congruent to 2 to the power 51, and write 2 to the power 51 in this form. So 2 to the power 10 whole to the power 5, that gives 2 to the power 50 into 2. So total 2 to the power 51. We are writing this in this form. Now 2 to the power 10 is already 1 modulo 11. So that 1 to the power 5, that is nothing but 1. This whole part becomes 1. So we are just left with 2 modulo 11. So 46 to the power 51 is 2 modulo 11, and 46 to the power 51 is 1 modulo 5. Now you use Chinese remainder theorem to solve these two equations. So there will be some x which is congruent to 1 modulo 5 and x congruent to 2 modulo 11. To solve these two modular so these two congruence, to get the solution as x is congruent to 46 modulo 55. You can check how the what is the exact algorithm of getting this solution of two congruent relation. So linear congruences, basically solving linear congruences with Chinese remainder theorem, you can check, and then we will see that this gives us the value that x should be 46 congruent 46 modulo 55. So we conclude that this result 46 to the power 51 is actually 46 modulo 55. Okay. Next question. So consider a secure PRF FK, which is mapping in-bit binary string to again in-bit binary string, using which we construct a queued function f dash, which is 2n size binary string maps to 2n size binary string, where f dash k for input x1 concatenated with x2 is defined as fk of x1 concatenated with fk of x2, and where x is x1 concatenated with x2. And of course, x1, x2 both are of the form in-bit binary string. Now there are some statements about security of f dash. So function f dash is a secure PRF, and when used directly leads to semi-secure math. Function f dash is not a secure PRF. Okay, so let's first analyze about the security of PRF f dash. So what you can observe is that you can basically so here the challenger, the PRF game between the challenger and adversary, the challenger may choose to output either the PRF evaluation on the query input coming from the adversary, or it may choose to output any random element from the output space, right? And the adversary basically has to distinguish whether it is interacting with a PRF oracle or a TRF oracle, like whether the outputs it is seeing for the query inputs, their PRF evaluation or some truly random value, output of truly random function. Okay. So what the adversary can do in the construction of f dash is that it can first query with some x1 concatenated with x2, some strings x1, x2 chosen by the adversary, and see the output. And then it can query with some x3 concatenated with x4, say, okay, and see the output. And then it queries with x1 concatenated with x4. And what is expected is that for the output, if the adversary is interacting with a PRF, like the challenger is outputting the PRF values, then what will happen in response of x1 concatenated with x4 is that it will match with the first part of the response of first query, that is f of k, f of x1 with respect to key k, and the second part of the output will match with the second part of the output for second query exactly, that is fk of x4, right? If this match happens, that means with non-negligible probability, the adversary is able to distinguish that it is actually interacting with a PRF, okay? And if it turns out to be some random string, the response of x1 concatenated with x4, then it will conclude that, okay, I'm interacting with a truly random function. Okay. So with non-negligible probability, it is able to distinguish between these two cases. So f dash is not a secured PRF, and as it is not secure, so function f dash, when used directly, that does not lead to a CMA secure map. Okay, so second and fourth options are the correct options. Now coming to this week's topics. So first problem that we discussed. So which of the following is or are true? First option given, hardness of the discrete log problem, CDH problem and DDH problem is in the following order: D log greater than CDH greater than DDH. Okay. So this statement is actually true. Okay. How? So as discussed in the lectures also. So what is discrete log problem? Basically, you have some cyclic group. Description of the cyclic group is available to you. Let's say there is some generator small g of that group, and you take some random power of that g, and that power, so let's say g to the power alpha, okay, is provided to the adversary, but adversary is unable to determine what is the exact value of alpha. So seeing the value of g alpha, what is the discrete log value? That is log of g to the power alpha with respect to base g. That is the value of alpha, right? So this logarithm calculation is not, so that is the problem, that you have to calculate the discrete log for the value g to the power alpha with respect to generator g, right? So that is the discrete log problem. And CDH problem says that you are provided with two values, like you have two distinct alpha and beta, and you don't know the value of alpha and beta, and you are just provided with g to the power alpha and g to the power beta. Now you have to compute the value of g to the power alpha beta. Okay. You don't know the value of alpha, you don't know the value of beta. You just know the value of g to the power alpha and g to the power beta, where g is the generator of the cyclic group, and you have to compute the value of g to the power alpha beta. So that is the CDH problem. Now, why we say that? So why we say that discrete log problem is harder than computational Diffie-Hellman problem, that is CDH problem? That is because let's say you are able to solve discrete log problem, so that will automatically imply that it is easy to solve CDH problem. Okay. So because if you are able to calculate alpha by seeing g to the power alpha, then when you are provided with g to the power alpha and g to the power beta, then easily you can compute alpha and beta, right? And then when you have knowledge of both alpha and beta, then you just raise g to the power of alpha beta, and exponentiation operation is easy. So g to the power alpha beta can easily be computed. So CDH problem becomes easy once discrete log problem is solvable, right? So that means that discrete log problem could be more harder than solving CDH problem. Okay. And similarly, once CDH problem is solved, so what is DDH problem? DDH problem is you are provided with a triplet of the form g to the power alpha, second element g to the power beta, and third element gamma. So third element, let's say R. Okay. So third element R could be either of the form g to the power alpha beta, or this third element can be any uniformly randomly chosen element from the group. Okay, the cyclic group we are talking about. So any uniformly random group element. So if so DTH problem is to distinguish this Diffie-Hellman triplet, which is of the form g to the power alpha, comma g to the power beta, comma g to the power alpha beta, that is Diffie-Hellman triplet, from any triplet of the form g to the power alpha, comma g to the power beta, comma R, where R is uniformly randomly chosen element of the group. Okay, so to distinguish between these two kind of triplets is the DDH problem. Now, once you are able to solve CDH problem, that is, you are able to compute the value of g to the power alpha beta, then you can easily check the third element is equal to. So, seeing a triplet, you can easily check if the third element is equal to g to the power alpha beta or not. Then, solving the CDH problem implies solving DDH problem. Okay, but not necessarily the vice versa. That's why we say that hardness wise, so hardness of these three problems are in the decreasing order of, so hardest problem is discrete log, then the CDH problem, and then the DDH problem. Okay, and then order of assumption strength. So which one is the weakest assumption and which one is the strongest assumption? So assumption strength wise, discrete log assumption is the weakest assumption. Why? Because discrete log problem is the most hardest problem, right? But now when you are designing a crypto system where you say the security of that scheme depends on the hardness, depends on the discrete log assumption, that means that if in that particular setting discrete log problem is hard to solve, then that crypto system is secure. And on the other hand, if the crypto system is based on DDH assumption, where the system is secure, if we assume that DDH problem is hard to solve in that setting, and as DDH problem is the believed to be easiest problem among these three, and the cryptography is not even, like, the adversary in that particular cryptographic setting is not even able to solve the problem, even when it is provided with the DDH problem, basically underlying assumption is DDH assumption. So in that setting, even the easiest problem is being hard for the adversary to solve. So that is the most strong assumption in terms of designing a cryptographic primitive. So that's why order of assumption strength is as follows: that discrete log assumption is the weakest assumption, then CDH assumption, and then decisional Diffie-Hellman assumption. So these two statements are true actually. Next, CDH assumption is true in a candidate group implies that DDH assumption is true in that group. So this is wrong actually, because we cannot say that. Rather, if we just said that if CDH problem is easy, that implies that DDH problem is also easy. So we cannot say that CDH assumption is true implies DDH assumption is true. Rather, it should be DDH assumption is true implies CDH assumption is true. That is, if DDH is hard to solve in a setting, then CDH is hard to solve in that setting. Okay. Next statement is CDH problem is easy in a candidate group implies that DDH problem is easy in that group. We have already discussed this. So this is already true. So the correct statements are the first one, the second one, and the fourth. Next problem. Given description of a group G, then this binary operator represented with a small circle, and then Q, and Q is the basically order of the group, okay, and G is the generator of the group. So that is the description of a group. Given description of a group and two random element alpha comma beta belonging to G, which of the following may represent Diffie-Hellman function? So 4 options are given. Diffie-Hellman function on alpha comma beta. One is G to the power alpha beta. Okay. Another is 8, this binary operator B with G, which means basically that so there can be two kind of group, additive group and multiplicative group. So by our notational convention, when we talk about multiplicative group, then applying the binary operator dot on the generator G itself, say I minus 1 number of time, will produce G to the power I in case of multiplicative group, that is by notation. So you are kind of multiplying G with itself I minus 1 number of times. So let's say G cube means G into G into G. So this operator, binary operator, is being applied twice. So that is G to the power I is applying binary operator on G itself I minus 1 number of times. So in case of multiplicative group, we denote that as G to the power I. In case of additive group, we will denote that as I dot G. So basically I into G. So that is kind of adding G with itself I times, or applying the additive operator I minus 1 times on G itself. So that notation is I into G, or in case of multiplicative group, it is G to the power I. So this is just notational thing, nothing else. Now, following that convention, Diffie-Hellman function is nothing but so provided alpha comma beta, that is alpha can be represented as some G to the power A, right? So alpha, if it is a group element, then it is some power of the generator G. So let's say alpha is G to the power A and beta is actually G to the power B. Okay, and Diffie-Hellman function actually computes G to the power AB, right? Or in other case, we can say that Diffie-Hellman function computes G to the power discrete log of A into discrete log of B. So third option is clearly correct. And if the group would have been an additive group, then it would be the fourth option, that is discrete log of A, binary operator discrete log of B into G. So that is the, in case of additive group, the expression should be like this. Okay. So third question. Let G be a prime order cyclic group of order Q with a generator G. Let H, which maps G to K, be a hash function modeled as a random oracle. Which of the following problems should be difficult to solve in G so that the probability distribution of G to the power alpha, G to the power beta, H of G to the power alpha beta is computationally indistinguishable from the distribution of j to the power alpha, comma j to the power beta, comma r, where alpha, beta are randomly chosen from ZQ and R is randomly selected from K. So if you would like to answer, then you can answer actually. I can pause for some time. CDH. Okay, that is true. Any other option you think? Log. Yes, you are correct. So let me just explain. So basically, if we want that these two distributions remain indistinguishable from each other, so let us think of in this way. So first thing, the D-log assumption is not true. That is, D-log is easy to solve. Okay. What happens in that case? Does it remain indistinguishable or not? So if D-log is easily solvable, then when you are seeing the triplets of the form j to the power alpha, comma j to the power beta, comma some third element, then see by seeing j to the power alpha, you can easily compute alpha, as we are thinking that D log is easy to solve. Okay, if that is the case, then you can easily compute j to the power alpha beta as well, because you know the value of alpha and beta by seeing j to the power alpha and j to the power beta. And as you can compute j to the power alpha beta, then you can compute hash of them as well. Okay, hash function is also available to you. Now hash of j to the power alpha beta, then basically it will not be anymore indistinguishable from any random element R. The adversary is able to compute g of h of j to the power alpha beta. So in order to maintain the indistinguishability, we need discrete log problem to be hard to solve. Also, in case of CDH, if we assume that CDH is easy, then seeing j to the power alpha and j to the power beta, it is easy to compute j to the power alpha beta, right? And once j to the power alpha beta is computed, then h of j to the power alpha beta is also computed easily. And in that case, again, we exactly know the third element, so it is not anymore indistinguishable from any uniform random element R. But in case of DDH, you cannot say something like that, because D just says that j to the power alpha beta is indistinguishable from any uniform random element of the if DDH is easy, then you can distinguish between j to the power alpha beta and some random element of the group G. Okay, but you cannot this cannot affect the fact that whether h of j to the power alpha beta remain indistinguishable from uniform random element or not. Okay, so we just need discrete log and CDH assumption to be true. That is, these two problems should be hard in the setting in order to maintain the indistinguishability between triplets of the form j to the power alpha, comma j to the power beta, comma h of j to the power alpha beta from j to the power alpha, comma j to the power beta, comma r. Okay. So, okay. Next problem. We want to build a PRG F ZQ square mapping to GQ, where G is a prime order cyclic group of order Q with a generator G, where D log CDH DDH assumptions hold. Let f of alpha beta is equal to j to the power alpha, comma j to the power beta, comma x, for what values of x the function f is not a PRG. So there are four options given: j to the power alpha plus beta, j to the power alpha, j to the power alpha beta, j to the power beta. If you would like to answer, give the answer. If we want some function to be PRG, that means that we are providing as seed, in this case alpha comma beta, and then we are outputting some larger length output which should be indistinguishable from any randomly generated string of same length. Okay. First two terms, j to the power alpha and j to the power beta, they are actually so these two parts can be anyway indistinguishable from random string, because seeing j to the power alpha you cannot guess anything about the value of alpha, right? So you cannot guess the seed. And our key point is about the third component x. Okay. So let us analyze these options one after another. So if x would have been j to the power alpha plus beta, how an adversary of PRG game, the PRG game is as follows: there is challenger and there is an adversary. The challenger chooses a bit B from 0 or 1 uniformly randomly. Let's say if B is 0, then it outputs the PRG output on some randomly chosen seed. Okay, let's say PRG of X. And if B is 1, then it will output some uniform, some truly random string of the same length. Okay. And adversary sees this output, which is generated by either the first method or the second method. And adversary's task is to output some distinguishing bit B to let the challenger know that yes, I am able to distinguish whether you are generating your output from a PRG or a TRG, that is truly random generator, either from pseudo-random generator or truly random generator. If adversary is able to successfully do that, that is distinguishing the PRG output from a TRG output, then the security of PRG is broken. Okay, now in case of first option, if x is equal to j to the power alpha plus beta, then what happens? The adversary just checks after seeing the output string whether the string x is actually value of multiplying the first two components. So j to the power alpha into j to the power beta is nothing but j to the power alpha plus beta. Right. So the adversary can easily check that whether the third component is the multiplication of first two component or not. If it is, then it will return that, okay, I am interacting with a PRG, pseudo random generator. And if it is not, then it will say that I am interacting with a truly random generator. And see, with this approach, the adversary is always able to distinguish these two cases with non-negligible probability. Okay. So first option is not correct. So it will not be a PRG. The second and fourth options are very obvious, because if x is equal to j to the power alpha, then obviously what the adversary needs to do to distinguish output of PRG from output of TRG is checking whether the first component and third component matches or not. In case of second option, so x is 0 to the power alpha, it will just check whether first and third component matches or not. And if it matches, then it will say that I am interacting with a pseudo-random generator. And if does not match, that is, it is actually a truly random string. So it will output that I am interacting with a TRG. And in case of fourth option, it will match the second and third component and outputs in the similar way. And in all these three cases, that is first, second, and fourth, the adversary is actually able to distinguish the output of TRG from output of TRG with non-negligible probability. So they are not secure construction of pseudo-random generator. In case of third option, just see, due to the DDH assumption holds, due to the fact that DDH assumption holds, then we know that due to the power alpha beta is actually indistinguishable from any random element of the group. So also, given due to the power alpha, you cannot compute alpha due to D log assumption. Same goes for computing beta from due to the power beta. So you cannot compute alpha and beta. Also, given due to the power alpha and due to the power beta, you cannot compute due to the power alpha beta. So you cannot check whether the third component is equal to due to the power alpha beta or not by seeing the first two component due to DDH assumption holds. And because DDH assumption holds, due to the power alpha beta will look indistinguishable from uniform random string. So basically, although due to the power alpha beta actually returns group element, particular group element, and group element, of course, the set of elements in the group is, of course, does not cover all the possible 0, 1 string on that output space. Okay, but still, by seeing only polynomial number of such samples, which comes either from PRG or from truly random generator, you cannot actually distinguish the due to the power alpha beta string from uniform random string of same Week-8. Okay, or truly random string. Okay. So we conclude that third option is the only choice where F will be a PRG. Okay. So answer is actually first, second, and fourth, where it will not be a PRG. Next problem. Assume two parties, P1 and P2, who are taking part in an instantiation of Diffie-Hellman key exchange protocol. They use an additive group G with generator small g and binary operator small circle. Which of the following statements is or are correct? P1 chooses random element R1 belonging to G and sends R1G equal to G applied with this binary operator with itself R1 times. That is the notational meaning of R1G. So P1 sends R1G to P2. Also, P2 chooses random element R2 belonging to G and sends R2G to P1. P1, after receiving some value alpha from P2, computes the key K equal to R alpha, where R belonging to G is some random element chosen by P1 in the previous step. And fourth statement is P1, after sending some value beta to P2, computes the key K equal to R beta, where R belonging to G is some random element chosen by P1 in the previous step. So basically, if you remember the Diffie-Hellman key exchange protocol, there is one interactive step where P1 sends something to P2 and P2 sends something to P1, and then they compute something internally depending upon the value received from the other party. Okay, so according to the Diffie-Hellman key exchange protocol with respect to some cyclic group G and its generator, okay, small g, all these things. So as it is additive group, so R1G is like that notation is given in the question. So first statement is obviously correct. So P1 will choose, actually according to the protocol itself, P1 chooses some random element R1 from the G, group G, and it sends R1G to P. Okay, that is the communication from P1 to P2. And similarly, P2 to P1 communication also includes choosing random element R2 from the group G, and this choice is made by P2, party 2, and then party 2 sends this R2G value to P1. Okay. So R1G, R2G are the communicated thing during the protocol. So first two statements are correct. The third statement says that P1 after receiving some value alpha from P2. So alpha can be of the form, say, R2G. Okay. So P1 receives something from P2, and after receiving that, how P1 computes the key? That is K equal to R alpha. Okay. So alpha is received from the another party, and R is some randomness chosen by P1 itself during the first step or in the previous step. So basically, if we map this statement with the first two statements, so P1 receives, say, R2G from P2 and then computes the key as R1, R2G, R equal to R1, because R1 was chosen by P1 in the first step. So R1, R2G, that is the key computed by P1. So this statement is also true. The next statement says that P1 after sending some value beta to P2 computes the key K as R into beta. So basically P1 sends beta to P2 and it does not calculate the new key using the value beta that it sends to P2, rather it computes on the value received from P2. So as the previous third statement said, that key should be actually R into alpha, not R into beta, because that would lead to beta is of the form R1G. Okay. So P1 sent R1G to P2. Now it is doing R into beta, that is R1 into R1 into G. So which is not, of course, some valid key, because in that case, P1 would compute R1 square G and P2 would compute R2 square G, which would not lead to some common key K. So the fourth statement is wrong actually. So first three statements are correct. Next problem. Which of the following are limitations of Diffie-Hellman key exchange protocol? The algorithm outputs any uniformly random element from the key space. The protocol requires both the parties to remain online during key exchange. The protocol does not provide security against active adversary. The protocol cannot be used in practice in its absolute form. The output of the algorithm is uniformly random element. If you would like to answer this. Answer. One, the algorithm outputs any uniformly random element from the key space. Actually, yes, 2, right. 2 is correct. So that is limitation actually, that during Diffie-Hellman key exchange, both the parties have to be online. Otherwise, this communication won't happen. And then each of them will be stuck if they don't get communication from the other party. 2 is correct, but 1 is not correct actually. The algorithm does not output any uniform random element from the key space. It outputs some uniform random element from the group, cyclic group that we are considering, right? So the group obviously does not cover all the possible, if we consider the binary representation of the group element, okay, so obviously the algorithm does not output strings from all possible binary strings of the output space, right? So it is just limited to the set of elements in the group only. then 3 can be also a limitation. Yes, you are right. 3 is also a limitation that protocol does not provide security against active adversary. So there is this man in the middle attack and all. So this kind of attacks are possible. If, so the assumption that seeing value of g to the power alpha and g to the power beta, you cannot guess the value of g to the power alpha beta or cannot distinguish it from the uniform random element of the group. That is just for the passive adversary. Active adversary can do something else also, and attacks are possible. Okay. So yes, 3 is also limitation protocol, and due to this limitations only, it is true that protocol cannot be used in practice in its absolute form. You have to modify the original Diffie-Hellman key exchange to make it used in practice in practical scenario. So and the last option that we are discussing, that output of the algorithm is uniformly random group element. So the correct options here are actually the all of them except the first one. The first one, it would have been the case that algorithm outputs uniformly random element from the key space, then that would not be a limitation. That would be advantage, but it is not the case. Okay. So what we can, how we can compensate that thing, that algorithm actually outputs uniform random group element. So both the parties now agree upon some common key, which is uniform random group element. Now we want the key to be uniform random string from the output space. Okay, so for that we can use some key derivation function, which they will just evaluate locally on both the sides and get some uniform random string. Okay. So anyway, apart from the first statement, all other statements are actually limitations of Diffie-Hellman exchange. Next problem, match the left column with right column such that the group in the left column satisfies the assumption in the right column. It is also mentioned that assume P to be sufficiently large and choose the strongest assumption if there are more than one. So I will pause for some time and wait for your answer. Okay, there is an answer in the chat. D maps 2, 2, 3, 4. Okay, there is a trick here actually. Yes, cyclic prime modulo elliptic curves with point addition operation, they are used as efficient candidate for this where these three assumptions are true. That is, all these problems are hard to solve. That is true, but the statement any actually does not hold. So there are certain conditions that which elliptic curve are actually usable or not. So there are some particular elliptic curves which are cyclic prime modulo curve with point addition, but they actually are vulnerable to attack. So for example, anomalous curves or super singular elliptic curves. So the general statement that any cyclic prime modulo elliptic curve may not hold all these assumptions true. So D actually should map to option 1. If this meeting ends, join in the same link. Okay, about the other options, you would like to answer A, B, C. What about C? P is given to be sufficiently large, right? And of course, P is prime. Okay, so let me just discuss that for the option C, actually, prime order cyclic subgroup of ZP star multiplication modulo P as the binary operator. So that okay, C is 4. C is 4 also. C is maps to 2 also. So strongest assumption actually is DDH assumption. So both these three assumption holds in case of C. If you have sufficiently large P, by sufficiently large, we have seen in the lecture that the uh, length of P, that is number of bits to represent P, if that is greater equal to 2048, so in the range of 2048 bit prime number, if we take, then any prime order cyclic subgroup of the form ZP star, okay, so subgroup of this will be actually satisfying all these three assumptions, DDH, CDH, and discrete log. And DDH being the strongest assumption, we will map C to 2 actually. Okay. And about B, so ZP addition modulo P is actually easy to solve even discrete log also. So the hardest problem, which is discrete log, is easy to solve in ZP. So all these problems will be easy to solve in ZP with addition modulo P. So B will map to 1, and ZP star with multiplication modulo P. This is actually, if you have followed in the lecture, so this group does not have prime order. Its order is P minus 1. So discrete log problem is not solvable here, but CDH problem can be solved in particular cases. So in general, we cannot say that CDH assumption holds. So only discrete log assumption holds in this case. So finally, A map to 4, B maps to 1, C maps to 2, and D maps to 1. Next problem. Choose the incorrect statements. A cyclic subgroup of ZP star with multiplication modulo P with P equal to RQ plus 1, where both P and Q are prime, having the form G equal to H to the power R mod P such that H belongs to ZP star, has order Q. So let us proceed the statement by statement actually. So the if we focus on the first statement only, so is it true or not? ZP star is P minus, has order P minus 1, but if we take some prime order cyclic subgroup of that, we are saying that P equal to RQ plus 1, Q is prime, and it is seen that the group G, H to the power R mod P, this has order Q, so that is prime order cyclic subgroup of ZP star modulo P. It has ordered Q, the statement. Okay, the second statement is that this group G, this prime order cyclic group, has a total of Q minus 1 generators. And third statement is that today's assumption holds true, for a prime order cyclic subgroup of ZP star multiplication modulo P with P equal to RQ plus 1, where both P and Q are prime, having the form H to the power R mod P with H belonging to ZP star. If size of P, that is length of bit representation of P, is greater or equal to 2048, if that occurs, then DDH assumption holds in those cyclic subgroups. Do you think any one of these statement is incorrect? Incorrect statement need to be chosen. Okay, actually, all the three statements are correct here. Okay, so they are just like proven theorem that if we form cyclic subgroup as written, that of the form H to the power R mod P, then that subgroup will have Q number of elements, that it will have order Q, which is prime order. And as you know that if a cyclic subgroup has this prime order, then except the identity element, all the other elements are actually generator of that group. So it will have Q minus 1 generator. That is also correct. And yes, for 2048 bit size of prime, that ensures that DDH assumption holds for those groups. Okay. So all these statements are correct. So the answer is actually none of the above. Okay. This is actually some descriptive questions. Okay. Determine the points on the elliptic curve given as y square equal to x cube plus 2x plus 1 over z11. How many points are there on the curve? So, okay, you cannot answer actually objectively. So let me just show how to determine points on elliptic curve. So elliptic curve has these points of the form x comma y, right? And both x and y will be from Z11 as we are considering elliptic curves in prime modulo. And y square, so this equation should be satisfied, of course, in mod 11. And there is additional point which we call point at infinity. Now, how many such pair x, y exist which satisfy this equation? You can simply first check that which are the square, sorry, which are the square residue in this group. So what that means is that basically for which value, which are the elements in Z11 that are perfect square modulo 11 for some element in Z11. Okay, so you just compute y square mod 11 for all possible value of y, that is 0 to 10. Okay, and observe y square modulo 11 for each of them. So 0, 0, 1, 1, 2, 4, 3, 9. 4 square is 16, modulo 11 is 5, like that. So you find that all these 1, 3, 4, 5, 9, all of them are actually quadratic residue modulo 11. Okay. And now computing x cube plus 2x plus 1 modulo 11 for all possible values of x, that is 0 to 10. So you just compute simply this value. So we get this value. Now we match that where this x cube plus 2x plus 1 mod 11 matches with y square mod 11. So here we have 1. So we will. So we have 1 here. So we will now observe that for which values of y square modulo 11 is congruent to 1. Okay. So here you see that for y equal to 1 and for y equal to 10, we have y square congruent to 1 modulo 11. So that is corresponding y value is 1 comma 10. That implies that basically 0 comma 1 is a valid elliptic curve point satisfying this elliptic curve equation y square equal to x square plus 2x plus 1 modulo. Okay. Similarly, here we get the value 4. That means here observe that 2 square mod 11 is 4 and 9 square mod 11 is also 4. So we write 2 comma 9 here. So for x equal to 1, possible y value can be 2 and 9. So like that we proceed. It's just simple calculation in modulo 11. And then we get this point. So 0, 1, 0, 10, 1, 2, 1, 9. For 2, we get this value as 2, and 2 is not a quadratic residue modulo 11. 2 is not here, observe. So we don't have any corresponding y value for x value 2. For x equal to 3, we got 1, 10 again. So 3 comma 1, 3 comma 10 is also valid elliptic curve points. Similarly, 5 comma 2, 5 comma 9, 6 comma 3, 6 comma 8, 8 comma 1, 8 comma 10, 9 comma 0, and 10 comma 3, 10 comma 8. All these are points on the particular elliptic curve. So how many number of points are there? If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and point of input. So total 16 points are there on this elliptic curve. Okay. So proceeding to the next question. Choose the incorrect options. Given a point P on an elliptic curve and O the point at infinity, P plus O is equal to P. So this is correct actually. So as you know, the point at infinity is the identity element of elliptic curve. Point at infinity is some like virtual point which is imagined to be lying on every y axis. Okay, so every value of y meets somewhere at infinity to some point O. Okay. Anyway, so that is the identity element for elliptic curve point addition operation. It is true. If p equal to x1, y1 and q equal to x2, y2 are two distinct points on an elliptic curve, and gamma is the slope, lambda is the slope of the line connecting p and q, then p plus q is x3 comma y3, where x3 is computed as follows: lambda square minus x1 minus x2, and y3 is computed as lambda into x1 minus x minus y1. This is actually true. We will see the computation in detail in the next slide. I will come to that. Next statement: p equal to x1 comma y1 is a point on an elliptic curve, and q is its x-axis reflection given by x1 comma minus y1. Then p plus q is equal to 0 comma 0. This is not true actually, because 0 comma 0 is not the identity element of elliptic curve. So basically p and q description given here, where the y1, so p is x-axis reflection of q and vice versa. Such two points actually are inverse of each other in the elliptic curve, in the group consisting of elliptic curve points with respect to point addition, and the identity element being the point at infinity, we can write p plus q equal to point at infinity actually, that is O, not 0 comma 0. And next statement: if p equal to x comma y is a point on an elliptic curve, then 2p equal to 2x comma 2y. This is also wrong, because the 2p is nothing but p plus p, and p plus p computation proceeds exactly as follows. In case of p plus q, the only difference is that in case of x1 minus x2, as x1 and x2 are same, so we can write lambda square minus 2x1, and y3 is exactly as written here. Only difference is that lambda value will not be same in case of statement 2 and in case of statement 4 here. So that will be different. We will just see the detailed calculation in the next slide. So point addition on elliptic curve. So curve is given as y square equal to x cube plus ax plus b. Also, we assume non-singular elliptic curve where the condition 4a cube plus 27b square should be not equal to 0. Okay. Now p is x1 comma y1 and q is x2 comma y2. And in case of addition, we first, so there can be three cases, right? Where first case is x1 not equal to x2. Second case is x1 is equal to x2, but y1 is actually minus y2. So y1 and y2 just differs in sign, not in value. That is the second case. And the third case is x1 is equal to x2 and y1 is also equal to y2. Okay. That is the value like x1 is equal to x2, y1 is equal to x2. So it is the same point basically. We are adding p with p itself. That is the third case. And there will not be any fourth case, which you can think of just the what if x1 is equal to x2 and y1 is not equal to y2, neither it is y1 not equal to minus y2. But that case cannot occur because if you see the elliptic curve equation, y square is equal to x2 plus x plus b, where y can be written as y equal to root over x cube plus x plus b. So value of y can be like for each value of x, there can be at max like two y values which can be just having opposite sign. So the fourth condition that you may think of, x1 equal to x2 and y1 is neither equal to y2 nor equal to minus. I think that will not happen. Okay. So let me proceed with the case 1. So x1 not equal to x2. In that case, how we compute the point p plus q? Okay. So first we assume some straight line y equal to lambda x plus c that intersects the elliptic curve in three distinct points. So the fact that the straight line will intersect the elliptic curve in exactly three distinct points, that can be proved. So we are not going into that. But just as we solve the what are the intersecting points of two curves, so the general methodology is applied here. So we just replace y with lambda x plus c here in the equation of elliptic curve. So lambda x plus c square equal to x cube plus x plus b. And you write the equation in this form, x cube minus lambda square x square plus a minus 2 lambda c into x plus b minus c square. That is the expanded form of this equation. Now, as you know that the coefficient of this x square here will be actually sum of the three roots of this. So x, this is the equation with power 3 of x. So the equation will have three roots in the form of x1, x2, x3. Now x1 and x2 are already known to us because we know the points on p and q on this straight line. So straight line is already intersecting the elliptic curve at p and q, and we are trying to find out the third point. So x1, x2 are already root of this equation. What is x3? So as lambda square is sum of the roots given, so lambda square we can write as x1 plus x2 plus x3. So x3 is written as lambda square minus x1 minus x2. That is exactly form what was given in your statement of the question. Now, to find y3, we just use the simple slope calculation of the straight line. That is, you have known point x1 and y1, and you know the value of the slope lambda. How you know the slope lambda? That is just, you have 2 points known, x1, y1 and x2, y2. You compute y2 minus y1 by x2 minus x1, generate formula for calculating slope of some straight line. So you know the value of lambda, and you know here the value of x1 and y1. So also x3 is known. So y3 can be easily computed as y1 plus lambda into x3 minus x1. So whatever x3, y3 value you get, that is the third intersecting point of the straight line with the elliptic curve, and the value of p plus q will be exact x-axis reflection of the point x3, y3. So whatever value you get by calculating x3, y3 in this manner, you just take x3, comma minus y3 as the value of p plus q. So that is how the point addition is performed in case 1. And then in case 2, where y1 is equal to minus y2, this case actually can be uh, handled by default, where we assume that such 2 points actually are inverse of each other, and their sum will be nothing but the identity element, which is pointed equal to. And in case of case 3, x1 is equal to x2, also y2 is equal to y2. So p plus p is being performed. And then x3, comma y3 are computed in the same manner as in case of case 1. So lambda square minus 2x1. Okay. And y3 is also similarly computed, but lambda, as you have the basically same point p, so you cannot calculate slope in the previous manner where you knew 2 points on the straight line, x1, y1 and x2, y2. Here you know only 1 point on the straight line, so you can just compute the slope of the tangent through that point on the elliptic curve. So the elliptic curve equation is y square equal to x cube plus x plus b. You compute the derivative dy dx, which is 3x square plus a by 2y, and you replace the value for point x1, y1, which is the known value on the straight line passing through it. So that is so the slope dy dx, or denoted as lambda, is computed as 3x1 square plus a into 2y1 inverse of 2y. So that's it. So that is how you compute x3, y3, and then finally you take the value of p plus b, or 2p, as x3, comma minus y3, because that should be the x-axis reflection of the intersecting point x3, comma y3. Okay. So next problem, let E be an elliptic curve over ZP for some time p, and consider the cyclic group consisting of the points of E along with the point addition operation. Which of the following cases lead to a group where Gradient's problem is easy to solve? We'll pause for some time. You can answer. Okay. So basically all the 3 options given are known to be not cryptographically secure elliptic curve to be used in practice. Okay. So mod E denotes the number of elements or number of points on that elliptic curve present in the group. So this mod E, if the size of E is equal to P for the prime number P, which the prime modulo P elliptic curve is defined for the same prime P. If that is equal to the elliptic curve size, then we are not supposed to use that elliptic curve in practice for constructing cryptographically secure primitives. And if mod E is equal to P plus 1, that is super singular curves, that is also should not be used. And because DDH problem is easy to solve them. Now, also if does mod E divides p to the power k minus 1 for small k. So all these three cases should be avoided. So last option is correct. Which of the following statements is or are true? Given the description of a prime order cyclic group, G, the dot operation, Q, the size of the group, and G, the generator, and uniformly random element H belonging to G, any element of the group can be represented in terms of G and H as follows. U equal to U to the power alpha, H to the power beta, where U belongs to G and alpha beta belongs to ZQ. This is the statement. The second statement is almost same. Apart from that, it says that any element of the group can be uniquely represented in terms of G and H as follows: U equal to G to the power alpha, H to the power beta. First statement just says that any element of the group can be represented in this form. The second statement says that any element can be uniquely represented in this form. And the third statement says that any element of the group can be represented in Q many different ways in this same form. Which of the statements are true? You can answer. Okay, so basically you have information about the generator G, and you are also provided with the uniform random element H, which is fixed. Now, any element of the group actually can be represented in this form G to the power alpha into H to the power beta for some alpha beta in Z. Okay. Now, this representation is possible. So first statement is true. Now second and third statement deals with whether it is unique representation or not. Second statement says that this representation is unique. Third statement says that there can be Q many different ways of such representation. Let us verify. So let's say you are given some representation U equal to G to the power alpha, H to the power beta. Now you can think of just changing the value alpha to some other value alpha dash. Okay, you can do that. Now you have some fixed value G to the power alpha dash, right? Now whether it is possible to have some beta dash such that U is equal to G to the power alpha dash and H to the power beta dash? Yes, it is possible because you are in a prime order cyclic group. So each of the elements in the group are invertible, and now for each value like G to the power alpha, for any alpha will map to some group element itself, okay, because of the closure property. And G to the power alpha is never equal to G to the power alpha dash, because if alpha and alpha dash are distinct, then you will have another unique beta dash when you are representing U as G to the power alpha dash, H to the power beta dash. So if alpha is not equal to alpha dash, then beta is also not equal to beta dash. Now there are, as alpha and beta, alpha and beta are chosen from ZQ. So there are Q minus, so there are Q number of possible values for alpha, and for each such possible value of alpha, you will have distinct value of beta such that this form of representation U equal to U to the power alpha, H to the power beta is satisfied. So there are exactly q number of alpha beta combination where alpha will have all the possible value, like some permutation of 0 to q minus 1, and beta will have also some permutation of value 0 to q minus 1 in each of such representation alpha I comma beta. And q such representation will be there. So third statement is correct and first statement is already correct. So just to mention with this discussion actually that this particular function like with given value of alpha and beta, the computation g to the power alpha h to the power beta, this value can be used in constructing cryptographic primitives like commitment scheme, more specifically Pedersen commitment scheme, also in computation of particular compression functions. So basically provably secure compression function and provably secure commitment scheme can be built upon the discrete log assumption basically. And also like the fact that if you are provided with two such distinct representation alpha I comma beta I and alpha j comma beta j such that u is equal to g to the power alpha I h to the power beta I, and also u is equal to g to the power alpha j h to the power beta j. So you have two unique representation of u in this form, then you will be able to compute the discrete log value of some particular g to the power alpha, right? So there is this game defined. So the fact that given g to the power alpha h to the power beta, an adversary is unable to come up with g to the power alpha dash h to the power beta dash such that alpha beta is different from alpha dash beta dash, is dependent upon the assumption that discrete log problem is difficult. And with such property, we can actually compute provably secure, we can come up with provably secure commitment schemes and also provably secure compression function. Compression functions are, if you remember, used in construction of hash functions for arbitrary length input using Martin-Temper. So next problem, select the correct statements. Perfect secrecy is theoretically achievable in symmetric key cryptography. Perfect secrecy is theoretically achievable in asymmetric key cryptography. COA security implies CPA security in case of symmetric key cryptography. COA security implies CPA security in case of asymmetric key cryptography. Single message CPA security implies multi-message CPA security in case of symmetric key cryptography. Single message CPA security implies multi-message CPA security in case of asymmetric key cryptography. You can answer this. This is the last question. So you can answer right away. Which of the statements are correct? Okay, let us see one by one. So perfect secrecy is theoretically achievable in symmetric key cryptography. This is true because we have already seen the OTP construction one time back, which is in symmetric cryptography and it achieves perfect secrecy. However, perfect secrecy is not actually achievable in asymmetric key cryptography or public key cryptography. COA security implies CPA security in case of symmetric key cryptography. COA security is ciphertext only attack, and CPA, as you know, chosen plain text attack. In case of symmetric key cryptography, both these concepts are actually different. COA, in case of COA, and eavesdropper just sees the ciphertext, and so let's say that ciphertext is either of message M0 or message M1. It cannot effectively distinguish whether it is encryption of M0 or encryption of M1. That is COA security. In case of CPA security, the adversary is actually given access to some encryption oracle where it can use the encryption oracle to see message ciphertext pair of messages of its own choice. Okay. So polynomial number of such message ciphertext pair you can see, and CPA security says that still the adversary should not be able to distinguish encryption of N0 from encryption of N1. That is the symmetric key case. But in case of asymmetric key, if you see that as in case of asymmetric key cryptography or public key cryptography, the adversary is already provided with the public key. Right. So with the knowledge of public key, it can actually itself generate ciphertext of any plain text as much as it wants, right? So it does not even need the access to encryption oracle. So whenever we talk about COA security and we provide the public key to the adversary, then the adversary already has default access to the encryption oracle. So it is not some explicit access to encryption oracle, rather it is implicit because it has the public key PK. It can choose any message of its choice and just compute the ciphertext on its own, right? So COA security implies CPA security in case of asymmetric cryptography, but not in case of symmetric cryptography. In case of symmetric key, the adversary need to be given access to encryption oracle explicitly in case of CPA security. And single message CPA security implies multi-message CPA security in case of symmetric key cryptography. This is true that we have already actually discussed in case of symmetric key cryptography. And the same holds for asymmetric key cryptography as well, that single message CPA security implies multi-message CPA security. So the true statements here are the first one, then the fourth one, and fifth and sixth both are correct. So that is all for today. I will end the session. Thank you for joining.